So when two things collide in an elastic collision, they just bounce off. No energy is lost in that collision. But in reality, collisions are inelastic. There is energy lost. And it's lost as heat. So when two gas particles hit, a small amount of their energy is converted into heat. Because when two things collide, they generate heat, always. So this is your ideal gas. This is what really happens. This is the ideal gas equation. So you're probably then asking, why do we even use the ideal gas equation if it only works for gases that really don't exist? Why don't we deal with reality? And the reason why we don't use the real gas equation is because two things. One, it's a lot more difficult. And two, it basically gives you the same answer as the ideal gas equation. So it's a very, 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 very good approximation. And the equation is a lot easier to use if you use the ideal. So let me just write down what the real gas equation is. So first, you have to take into account the volume of your gas. And I'll put that back up in a second. If I wanted to find this volume, what would I do? Length times width times height, right? That's not too hard to do. But what if I wanted to find this volume?
Well,
what if I had to take into account the fact that these gas molecules took up space? I'd have to subtract what? How many gas molecules I have times their size. So maybe we should write it on this handout that I gave you. So N would be the number of moles, and B is the size of your gas particle. So we'd have to subtract out the blue portion. Well, it doesn't look too bad. But the attractive forces change the pressure. So we're going to have to adjust our pressure. Just like people, different gases are more attractive. Really attractive gases have really strong attraction. So you're going to have to measure the attractive force. And it depends on the density. The way I put it is, suppose you have a dance, and there's 100 people at the dance, and you're at Lambeau Field. You're not going to run into anybody, okay? It's too big of a place. So the chances of you actually being attracted to and colliding with somebody, very small. But if we took 100 people and we put them in this classroom, well, the odds of you bumping into somebody is much higher. So we need to know the density, so moles per volume. Moles divided by volume would be your density. And attraction is mutual. So when I'm attracted to the Earth is attracted to me, the attraction is squared. Equals nRT. So it's V minus NB in parentheses times P plus A over N squared over V squared equals NRT.
Is the N over V, is that like this?
That's multiplied by A.
Okay, so it's not like
Right.
Is this on an appendix?
Nope.
That's what this number is.
And the reason why this isn't on an appendix is because in this class you will never use it. In AP Chem, we will. But as you can see, this equation is a lot more difficult than the ideal gas equation. And this is the one few times that I can actually say the equation's a lot more difficult than it looks. If you try to solve for V, you'll end up with a trinomial. And then you'll have to use some pretty clever mathematics to solve the trinomial. So we don't use this equation. Even though this is the correct equation and it's an accurate representation of reality, we don't use it because even if you use this one, it is within like 90.9% accuracy of this one. So why use this really difficult equation when this one will get us within like 0.1% of the real answer? Actually, even closer than that. So the ideal gas equation is a very good approximation for what really happens. And you don't need to know what type of gas it is. All you need to know is the number of moles. You don't need to know if it's helium or nitrogen or chlorine gas. The real gas equation, you need to know which gas it is because you need to know the size of the gas and you need to know how attractive the gas is. So ideal works just fine. You only need to know, you only need to use the ideal gas equation, the real gas equation under very high pressures. So under very high pressures, you need to use the real gas equation. And the way the two differ, if you were to graph 1 over P using this equation, it would go through the origin. So if you graphed PV equals nRT, that's what you'd get. If you use the real gas equation, it will look identical, except for at the very, very end, it'll curve and tail off like that. So the two equations give you identical answers except at the very end. Because, of course, you get to a certain point where you cannot compress the gas anymore. Because if you try to, I'll put that back up. What happens if you try to compress a gas? Eventually it'll turn to liquid and then solid, and then you can't compress it anymore. So you cannot compress down to zero like an ideal gas. You can only compress to a certain level. Yep.
We use ideal gas under like low pressure.
I would say normal pressures. Actually, I would just say any time except high pressure. So you can use the ideal gas equation anytime except for high pressures. So once again, you're never going to use the real gas equation in this class. That's why it's not in your appendix. But when you take AP Chem, you will get the enjoyment.
Joke's on.
Joke's not on. Any other questions?